Hello everyone and welcome to the channel. Today we're going to build a classic but very useful project, a flasher for LED signs. As you can see, the heart of our circuit is this small chip, the CD4093, and a power transistor, the TIP41. This circuit will allow us to make a series of LEDs blink, ideal for decoration projects, signage, or simply good for learning how these integrated circuits work. That's why we're not only going to assemble it, but we'll also look at how it works in detail, even using the oscilloscope to see the magic of the waveforms. I'm Caesar, and I warmly welcome you to my channel. All right, now let's go to our circuit. Let's analyze the heart of this project. Here we have the schematic. Let's divide it into two main parts, okay? The oscillation stage and the power stage. The oscillation stage is built around the integrated circuit CD4093VD. This is a CMOS chip that has 4 components with Schmitt trigger action. What makes a Schmitt trigger special is its hysteresis, which makes it immune to noise and perfect for creating oscillators. By connecting the 10 microfarad capacitor and the resistors R1 and the 10K potentiometer, we form a stable oscillator. This means that the circuit will generate pulses continuously without the need for an external input. What the potentiometer does is allow us to vary the frequency of the pulses, thus controlling the blinking speed. As I mentioned before, the CD4093 has 4 N and D gates. In this case, we use one, but you could use all 4, and with a circuit equivalent to the one we're making in each of the gates, you could control 4 LED strips. In this case, well, to simplify things, I only used one gate. The square wave signal generated by the CD4093 won't have enough power to turn on the LEDs directly. That's why we use the power stage, which is this one, and it's made up of the TIP4043. This is a power NPN transistor that acts directly as a switch. It's important to know that this transistor has a maximum current capacity of about 6 amperes. So, well, keep that in mind to determine how many LEDs or how many meters of LED strips we're going to use. Also, it has a power dissipation of 65 watts. So normally a heat sink is required in these applications to prevent it from overheating. When the signal from the CD4093 is high, the transistor is activated and allows current to flow from the 12-volt supply through the LEDs, turning them on, of course. Well, when the signal goes low, the transistor turns off and the LEDs turn off. If you want to make the blinking slower, you can increase the value of the 10 microfarad capacitor. You can use a bigger one. In this case, I used a 33 microfarad one because I wanted to make the blinking more noticeable. With an understanding of the circuit, it's time to look at assembling the board, which takes us about 5 minutes. It's really fast because everything is marked perfectly labeled where you have to put each part. You just solder the components. I've placed the CD4093 in a socket. 2 resistors, the capacitor, the transistor, TIP41. As you can see, they're very important. There are very few components, and in a second, you have everything soldered. We connect the power supply and, of course, the LED strip. And there you have it. The circuit is working perfectly. As you can see, with the potentiometer, we can control the blinking speed. And this is ideal for bringing any illuminated sign to life. Now comes the most exciting part. Let's look at the signals in real time on our oscilloscope. This allows us to understand in a very visual way how the circuit works. First, let's connect the probe to the output of our oscillator stage, which is pin 3. Or if we see that it's difficult to place the probe there, we can put it directly on the base of the TIP41.
41.
When the potentiometer is at one end, the frequency is low and the wave is wide. As I turn it, the frequency increases and the wave becomes narrower, which corresponds to a faster blinking. Next, connect the probe to the power output. Where the LEDs are, we're going to connect the other channel of the oscilloscope. Notice how the wave in this version is amplified. And it's inverted compared to what we saw at the base of the transistor since it's acting as a switch. This demonstrates how a small signal can control a higher power circuit. Well, I hope this project has helped you understand a bit more about oscillator electronics and how a simple chip like the CD4093 can control a power circuit with a transistor like the TIP41. See you in the next video, God willing.